This video is brought to you by Nebula, where you can watch our bonus videos featuring F-16 test pilot David Carr by signing up for only $2.50 a month. A fully loaded F-16 is a formidable air superiority machine, relied upon by nations worldwide to patrol their skies. Designed as a low-cost, lightweight, single-engine fighter, it was built to outmaneuver opponents while carrying advanced missiles, ideally never needing to engage in close combat. The F-16 emerged from the lessons of the Vietnam War, where large, heavy, complex U.S. fighters like the F-4 Phantom struggled against smaller, more agile Soviet-made MiGs such as the MiG-21. The MiG-21, a compact, single-engine aircraft with thin delta wings, exposed the F-4's vulnerabilities. Despite the force speed of Mach 2.2, long range, and powerful radar, its lack of maneuverability at low speeds, poor pilot visibility, and telltale black smoke trails made it an easy target for the MiG-21 sneak attacks. The MiGs often flew low to avoid radar, ambushing F-4s with infrared-guided missiles before escaping with superior low-speed maneuverability. From August 1967 to February 1968, U.S. losses were staggering, with 18 aircraft lost compared to just 5 enemy planes downed. For a nation accustomed to air dominance, this was a wake-up call. The introduction of the MiG-21 in 1966 forced the U.S. to rethink its approach. Large, heavy fighter bombers, while versatile, were outmatched by smaller, cheaper planes. The Red Baron study, commissioned by the U.S. military, analyzed the tactical and technical issues behind these losses, leading to the development of one of the world's most iconic fighter planes. Entering service in 1978, the F-16 has stood the test of time and is now set to play a crucial role in Ukraine's fight for freedom, taking on modern equivalents of the MiG-E. The F-16 was designed around a classified 1966 paper by Colonel John Boyd, a Vietnam War veteran and member of the fighter mafia, alongside civilian mathematician Thomas Christie. Using military supercomputers, they developed the energy-maneuverability theory, a physics-based approach to winning close-quarters dogfights. This theory focused on managing a plane's kinetic and potential energy, speed, and altitude to outmaneuver enemies efficiently. The F-16's energy maneuverability diagram, though complex, illustrates its capabilities. The diagram's maximum lift line determines the plane's turn rate at various speeds. For example, at 0.4 Mach, the F-16 achieves a maximum turn rate of 13 degrees per second, compared to the F-4 feet seconds 5 degrees per second at the same speed. For sustained turns without losing altitude, the F-16 achieves 14.2 degrees per second at 0.85 Mach and 7 grams, while the F-4 manages only 10 degrees per second at 5 grams. In practice, this means the F-16 completes a 360-degree turn in 25 seconds, 11 seconds faster than the F-4's 36 seconds. The F-16's design philosophy prioritized maneuverability in the transonic range of 0.8 to 1.2 Mach, where most dogfights occur, rather than chasing Mach 2 speeds with limited tactical value. Its engine inlet, a flat-faced pitot design, reflects this focus. Unlike the F-4's extended inlets, which attach a shock wave to manage supersonic airflow, the F-16's inlet is optimized for subsonic and transonic speeds. This ensures the engine receives subsonic airflow, preventing damage to the turbine, though it's less efficient above 1.2 Mach. The inlet's placement under the fuselage, combined with a thin, elongated wing and leading-edge strakes, ensures the engine gets sufficient air during high angle of attack maneuvers. However, this low-mounted inlet, just 100 centimeters off the ground, posed challenges for landing gear placement. The thin wings couldn't house the gear, and placing it ahead of the inlet risked debris ingestion. Instead, the gear is stored behind the inlet with a unique folding mechanism to widen the wheelbase for stability. The front landing gear rotates 90 degrees to lie flat under the inlet, and a boundary layer diverter channel prevents turbulent air from entering the engine, reducing performance loss and fatigue on turbine blades. The F-16's leading-edge strakes, blending into the fuselage, enhance lift during high angle of attack maneuvers, similar to canards on planes like the Su-34. These strakes create vortices that maintain high-energy airflow over the wings, delaying stalls. During development, General Dynamics tested various configurations in wind tunnels, consulting NASA to sharpen the wing's leading edge for stronger vortices. This design also provided space for the F-16's 20mm M61 Vulcan rotary cannon, a critical feature absent in early F-4 South. The Red Baron study highlighted the F-4's lack of an internal cannon, leaving it vulnerable in close-quarters combat. The F-16's M61, a smaller version of the A-10's GAU-8, fires 120 rounds per second, emptying its 511-round drum in just over 5 seconds. Tucked neatly into the fuselage to minimize drag, the cannon's vibration is intense, with pilots describing it as a chainsaw in your left ear. During training, new pilots often find their first strafing run overwhelming, with the jet shaking violently as foam insulation flakes off from the vibrations. The F-16's leading-edge flaps, which deflect downward during high-angle of attack maneuvers, further enhance lift by 18% and reduce drag by 22% at 0.9 Mach. Actuated by hydraulic motors and torque shafts, these flaps are controlled automatically by the F-16's fly-by-wire system, a groundbreaking feature at the time. Unlike the F-4's heavy mechanical control system, which used cables, rods, and a 2 kg bob weight to provide feedback, the F-16's fly-by-wire system relies on sensors, wires, and computers. Early F-16s had an immovable side stick, a force-based inceptor adapted from the F-111, but pilots struggled with its lack of proprioceptive feedback, leading to pilot-induced oscillations, PIO. Later models introduced slight stick movement to address this. The F-16's intentional instability, achieved by placing the center of lift ahead of the center of gravity, reduces the energy needed for maneuvers. Unlike the F-4, which wastes energy on downward lift from its horizontal stabilizer, the F-16 stabilizer generates upward lift, increasing turn rates. However, this instability requires constant corrections, managed by the fly-by-wire system's accelerometers, gyros, and airspeed sensors. This instability was evident during the YF-16 prototype's unintended first flight, where control logic issues caused excessive thrust and roll oscillations. The fly-by-wire system limits the F-16 to 9 grams and 26 degrees angle of attack, preventing structural damage or loss of control. The cockpit, with its 30-degree reclined seat and side-mounted stick, enhances pilot comfort and jet tolerance. The recline reduces the heart's effort to pump blood to the brain by about 1 gram, while inflatable bladders limit blood pooling in the legs during high-G maneuvers. The bubble canopy provides 360-degree visibility, critical for situational awareness. Despite being a 45-year-old design, the F-16 remains relevant, with the U.S. Air Force planning its use until 2048. In Ukraine, it will support ground troops and carry cruise missiles, leveraging its maneuverability against Russian defenses. Our interview with test pilot David Carr provided invaluable context, including details on an automatic obstacle avoidance system that uses terrain data, not radar, to save lives. You can watch this bonus content on Nebula for $2.50 a month, along with ad-free versions of our videos, originals like our World War II logistics series, and content from creators like Mustard and Practical Engineering. Nebula offers a seamless, ad-free experience, perfect for downloading videos for offline viewing, and supports our channel at a fraction of YouTube Premium's cost.